All right, so today we're going to get into percent dissociation. So percent dissociation is the percent of acid or base molecules that ionize when we put them in water. So for percent dissociation for a strong acid or strong base, then that would be 100% because they completely dissociate, they completely ionize. But for weak acids or weak bases, it is a much lower percentage. So the way we find this, and I know it's a little bit hard to read, but it's the H plus or OH minus concentration divided by the total concentration or the initial concentration times 100. So in this case, a lot of times you're going to have to find the H plus or the OH minus concentration in order to figure out the percent dissociation, because these will not be given to you. You might be given the pH, or you might be given the initial concentration and a Ka or something like that. But a lot of times you will not be given the H plus or the OH minus. You got to calculate that. So here's an example. What is the percent dissociation of a 0.4 molar solution of boric acid? So if we think about boric acid is this, and if we write out the equilibrium or the equation, it's going to be H3O plus H2BO3. Okay, and what do we know if we do ice chart? I know this is 0.40. I know this is, the water's not going to matter. We don't need it in our equilibrium expression. We know those are 0. So this will be minus x plus x plus x, 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 and then 0.40 minus x. Okay, so this is similar to how we've been setting up these problems. And then my expression, Ka equals H3O plus H2BO3 minus over H3BO3. Okay, and I know this seems repetitive, but make sure you write out the expression each time. Get in the habit of doing that, because again, it's going to be helpful to you. So then we plug in our numbers. So this is basically x squared at the top equals 0.40 minus x. And that equals the Ka of boric acid, which is 7.3. You look on your Ka chart, 7.3 times 10 to the minus 10th. Now we know that 0.40 minus x is approximately equal to 0.40 because x is going to be very, very tiny. So we can ignore this x, the minus x. So we end up with x squared over 0.40 equals 7.3 times 10 to the minus 10th. Then if I multiply both sides by 0.40, so I'll do that in my calculator. So 7.3 e negative 10 times 0.40, I get 2.92 times 10 to the minus 10th equals x squared. And then I do the square root. So square root of both sides. Not that one. Square root 2.92 times 10 to the minus 10th. And let's put it in scientific notation. So x equals 1.7 times 10 to the negative 5th, okay, which is equals my H3O plus concentration. Okay, so then if I know that, I'm going to plug it back into this formula up here. So I know my total, or my initial concentration is 0.40, so that's the total, that's the part over the whole. I mean, this is the whole. and I know my H plus concentration is this. I'm going to do is the 1.7 times 10 to the minus fifth, and then I multiply that by 100. So I'm going to do 1.7 times 10 to the minus fifth divided by 0.40 times 100. And so it is 0.0043%. So we're talking a very, very tiny percentage, right? And that's what you're going to get most of the time with these weak acids or weak bases, because they don't ionize very much. If you think about, this has a Ka value of 7.3 times 10 to the minus 10. So very little on top and a large amount on bottom to get a number like that. So you should expect percentages to be pretty small. All right, I hope this helps. Let me know if you have any questions.